Okay, let me now get to the punchline for this section, and I'm going to now tell you what a surface integral is. So as I outlined, a surface integral will look something like f dot ds, where I'm using shorthand to say this is a normal vector times that area. And it's a natural quantity because whenever you have a ds, there's always some oriented unit normal vector that goes along with it. And although you won't actually need this in calculations a lot, because I think it's not very practical, I think this quantity, it actually has it has a much nicer interpretation. So for comparison, I'm going to go back to 1D. Remember, right now we're in a 2D setting, and let's look at line integrals for a sec, involving work, the work kind. So these integrals look like this. It's the integral along a closed curve of f dot dr. And remember, dr was r prime of t dt, where this was, in if we parameterized it, our curve. But so it's natural to wonder if ds has a similar interpretation. So actually, I claim that ds is r, some derivative of r times du dv. In fact, it's ru cross rv times du dv. And it's the natural generalization of that 1D formula. Notice, of course, that the u and the v, they cancel, just like dr dt cancels with that differential. And it also has the right dimensions. It's dimensions of meters squared because we have two r's, and in this case, the dimension is meters, and it's compensated for by that derivative. And so now let me show you why this formula works. So the formula works. And also let me just emphasize one more, that ds with a vector sign, it's an actual vector times the differential. And we have the differentials, and here are the vectors. The cross product is a vector. It's the dot product that's a scalar. That is, it's just a number. The cross product, in contrast, is a vector. So that should explain why all this notation makes sense. So now let me just get back to why is this formula even true? Well, we know ds is actually that normal vector times the area, so all we need to do is just evaluate this area thing. So it's that ru cross rv thing, that parallelogram area, times that square area if we in the parameterized variables. So now we're just going to use what we found in the previous video for that normal vector. It's actually the cross product of those two tangent vectors. In order to make it a normal vector, we divide by that length. So you see what happens here, right? As always, in these kinds of problems, we get some kind of cancellation. So we end up with what we want. And I'm skipping the fact that we have actually some kind of plus or minus sign here. And this is for the orientation. And for closed surfaces, we're always using the outward orientation. And by closed, I mean things like spheres, I mean cylinders with tops on them, and so on. So that explains why we get these nice formulas. And it's all because the normal vector denominator cancels with that area factor. I think it's pretty cool. And the one thing I'll mention, though, is that this is not always practical. I mean, often it saves you a step. Right? Like, so you don't need to get that length of that cross product. So that's good. But it's not always practical because sometimes is hard. And in fact, in the sphere case and in the cylinder case, in my previous videos, the way I did this was I used the fact that these lengths are actually, they split because the dot product is 0. And so this is much easier. And also, to get these normal vectors, it's also, you can kind of just do this by inspection. And what I did was I verified. In my previous video, I verified that n times the tangent vectors is equal to 0. And this is another equivalent way. Which does not use the hard cross product. So if you haven't seen those videos, definitely check them out because nobody likes doing cross products. And so any way to avoid that is always good. Okay, hope this was helpful. Thanks for watching.